So today we're going to review a little bit from what we've seen last lecture and move a little forward. Okay. What we done last class, we are studying, the trajectory of a projectile, right? The first thing we did is we using 4 of these equations that we studied already. So this is basically an application of the equations that we came up with, right? So the first thing we did is I showed you by calculating time on equation number 1 and plug in on equation number 3, basically finding y, this is the y-axis, as a function of the x-axis, right? So this is distance on the vertical and this is distance on the horizontal. And the equations have time on it. So I have to remove the time from the equation, right? Plug in x on this equation. This way I could have y as a function of x, that is this one, and I showed you that it's a quadratic equation. So this curve, it is a parabola, and because of a negative sign here, we have a maximum here, okay? So instead of a u, parabola, u, we have a maximum, like a mountain, right? So was this clear for everyone, right? To understand that, this is in fact a parabola, yeah. The K, yeah. Remember, it is in my notes that I posted also on Canvas. This K was a bunch of constants, sine of an angle, the acceleration of gravity, those are all constants. So to simplify and to make easier for you to understand that this is a quadratic equation, I just put a constant here. A quadratic equation should look like this: y ax squared plus bx plus c. What is a? It's a constant. Sorry.
Now it's working.
Some,
It just let me go. No, it does not sign in.
don't forget to turn off your cell phone. All right. So this is also a constant. This is a constant, right? So that's it. It could be like B here and A there. And just put K1 and K2, 2 different constants. Is that okay?
Yeah.
So what was the next thing? The next thing we did is from here, I calculate the time, okay, for the highest point. At the highest point, the speed on the y-axis is going to be what value? Once it reaches the highest point, what's going to be V final here at this point? Huh? 0. H is the height. H is the highest point, is this point, okay? Now, if you look, I'm calculating time from this equation, okay? And then what I did is I plug in this value on the second equation, okay, to calculate the height, because y is the distance in the vertical direction. At the end of the class, we were discussing a little bit about substituting the time. You cannot calculate the time for one equation and plug in on the same equation. It's not going to work, right? You remember when you solve a system of equations? Like for instance, if I have x plus y equals 5, and then 2x minus y equals 7. And I say, solve this system of equations. What do you guys do? by the substitution method, what would you do?
Well, in this one, you can just add them, because the y's would cancel out.
Okay, let's use the substitution. I know it would be, let's make it a little difficult then. Let's put 3 here, okay? So if you could multiply here by 3 and then add, that's the addition and elimination method, but I'm asking for the substitution method. What would I do? Yes.
You can solve for x in the first one and plug it in.
Exactly, I can solve for x here, and this is gonna be 5 minus y, right? And then, I'm gonna plug this in the odd equation, right? We cannot plug this in on the same equation. Do you remember at the end of the class you were asking me that? That's what was happening, you know. You were calculating d, and then we are plugging in on the same equation, and you wouldn't go anywhere, right? Because it is an identity. If I just plug this in here, it's not going anywhere. Is that okay? So if you observe, that's what we're doing here. So I'm calculating d on this equation, then I plug in here to eliminate the time so I can get the height. All right? So this is the height. Okay? Now, what's going to be the maximum height? If I put this vertical, we just did this experiment, right? We calculated about 3 times what would be the right. If I make this angle 90 degrees, the sine of 90 is 1. So now the equation becomes h vertical. This is the vertical tree, right? Is going to be v0 squared divided by g. So what is this equation going to allow me to do now? What do you think?
Calculate the height.
Huh?
Calculate the height.
We measure the height. What are we going to measure? What are we going to calculate here?
Initial velocity?
Huh?
Initial velocity?
The initial velocity, right? We're going to calculate v0. So we figured that we had 2.2 meters, 2.1, and then 2 point, right? So the average here is going to be 2.1. And we need to estimate an error, right? What would be going plus or minus 10? Let's do plus or minus 0.15. Okay? Now, how much is that in percentage? Let's calculate here. Cell phones are wonderful, you know? So it's 0.15 divided by 0.1. So that's about 7%. 7% error, okay? Is that good?
Where did you get the 0.15 from?
Well, this is 0.1, this is 0.1. I just, you know, giving a little more on both sides, because we just did 3, right? We saw it was varying a lot. So I'm just putting an extra.
Okay, so it's not like an exact value, but what kind we're estimating earlier.
We're estimating a little, you know, giving us some more margin for error here, okay? It's better to be on the high side than on the low side, right? Okay. So, having this number now, I'm going to multiply times g, and that's going to give me v0 squared, right? v0 squared is going to be 2.1 times 9.8, and that makes 20. Is that okay? let's see. By the way, I made a mistake here. There is a 2 here, okay? There is a 2 there. So there is a 2 here. So this value should be times 2, 41, 16. So V squared is 41, 16. Okay? Let's save that number. Now, the next step is going to be what I asked you at the end of last lecture was to calculate OS. And OS is this distance here. We have D1. D1 is this guy here, right? D1 is this guy. So if this is symmetrical, D2 should be 2 times this value. Okay? 2 times that value. So let's write that down. So D2 is going to be 2 times V0 sine alpha divided by G. Okay? Now, to calculate OS, what we need to do, we already have time, D2. What we need to do now to calculate this distance? Which equations should we use? Three? What is 3? 3 is Y. Y is the vertical direction, right? I'm asking you to calculate
The second one.
OS, the distance,
The second one.
OS. Huh?
Second one.
The second one, this one? This one is the speed, right? This here is the speed. Is number 1. Who said number 1? Yeah. Why number 1? Because number 1 is x minus x0. x0 is here. This is x. So we use this formula here. Okay? So what we have? We have x minus x0, that is OS. Okay? And that is equal to VOXT. But what is VOX? VOX is V0 cosine alpha. So we have here V0. This is VOX is the projection of the initial velocity on the x-axis. Is that clear? And VOY is the projection on the y-axis. So if I'm asking you to calculate this distance, you need to involve the x-axis, speed, and the time, right? Is that okay? Speed times the time give us the distance. So OS is going to be the speed on cosine alpha times the time is here. Is that okay? This number, 2 VO sine alpha divided by G. Now this is going to come out to be VO squared 2 cosine alpha times sine alpha divided by the gravity, okay, acceleration of gravity, okay? Now, from the trigonometry, we know that this here is going to be equal to V0 sine 2 alpha G, okay? I put also a file on Canvas on trigonometric functions. So if I have sine of alpha plus beta is going to be sine of alpha times cosine beta plus cosine alpha sine beta. Now, if these two are the same, so you're going to have sine 2 alpha is going to be equal to 2 sine alpha cosine alpha. And that's this here. Is that okay? Yes.
If you were to apply this to a real problem, could you just solve in parts and plug in instead of making a giant equation?
Yeah. Yeah, you can do that. Okay, so we're gonna apply this now to a real problem. I'm coming up with this so I can show you. I want to make a prediction here. Where is this, when I release this ball, what is going to be the initial velocity here now? Do we know the initial velocity here? What is this value? V0 squared, right? We just calculated that. We measure the height and we calculate V0 squared. What we need here, we need V0 squared. Can we plug in this number here for a certain angle, and then we're going to have what? We're going to have a prediction of where this is going to start, right? Can we calculate that now? Let's say I set this up here to 45 degrees. 45 degrees times 2 is going to be? 45 times 2 is? 90. Sine of 90 is? 1. So I'm going to have to divide 41 by G. And let's see how much that's going to be. 41.6G divided by 9.8. That makes 4 meters and 20 centimeters. Okay? So OS for 45 degrees is going to be 4.2. If I change the angle to 30, then it's going to be 2 times 30. We have to calculate the sine of 60, right? 2 times 30 is 60. Sine is 60 times V0 squared, that is this value here that we calculate, divided by G, and then I'm going to have a different prediction. So tell me, if I calculate for 30 degrees, is OS going to be larger or smaller?
Smaller,
Smaller. Why?
because 60 is a small number. The sine of 60 is going to be smaller than the sine of 90.
Exactly. Okay? If you guys remember the trigonometric circle, the sine is this height here, right? When this angle is exactly 90, the height is the radius of the trigonometric circle, that is equal to 1. So if I say 60, this height is going to be less than 1. Okay? If it's less than 1 times this divided by that, it's going to give me a number lower than 4.2. Yes?
Is the initial velocity going to be the same?
The initial velocity,
Yeah, is it going to be the same? Are we going to be able to use that number?
V0 is the initial velocity.
Yeah, but you're using that number to
I'm
solve this,
using
right?
the V0 squared. I can calculate V0. Let's calculate V0. So it's 41.16 square root of that. So V0 is 6.41 meters per square. That is V0, but this here is V0 squared.
Yeah, I understand that, but let's say I'm doing like another problem. Can I use that number or,
This number?
yeah,
Well, if it's a different problem, it might be a different
yeah.
condition, right? It might be a different velocity. This problem, we measure,
Can
right? We
can
measure the height, and by measuring the height, we calculate V0 for this problem, right? If it's a different spring, might be a different velocity.
Can we do like different problems instead of the formulas? Cause it's making me confused. It's confusing.
I know. I hope you understand the purpose of this is to see how we can manipulate these equations to calculate different things, like the highest point here, right? For the distance, we want to know where this bullet is going to land on the ground, right? Anybody in the military here? So, yeah, you know, that's how they calculate things, right? When they shoot something, right? So, are you guys excited about this? Is it interesting?
No.
So, is this estimate 4.2? Let's measure that and see where that is, and then we shoot and see if it's gonna hit that value. Is that okay? So let's see. This is 2 meters. This is 4 meters, and our estimation is gonna be 4.2. So, so maybe you focus the camera where it should be. So I'm going to put here 4.2. Is that 4.2? Yes. 4.2 is right
Sorry.
here.
Oh my God.
So that means 4 meters and 20 centimeters. And we have a plus or minus arrow here. If we estimate the arrow here by 1 degree plus or minus, if you calculate the sine of 60 and the sine of 58, you're going to see that this is going to be about another 2%. So 2% plus 7% makes 9% of error. So we need to calculate how much that's going to be on here, so I can plug in my tolerance here, right? So let's figure out how much is going to be 9%. 9 times 4.2. That makes 37. So I'm going to set this around here, 37. So 20 plus another 10, and then 20 plus here. So this is our main estimate, and those are my tolerances. So hopefully that ball will land somewhere here. So I need another volunteer to stay here and point where the ball landed. Who wants to come? You want to come? He's always the volunteer, right? And somebody look for the ball too. I want to.
Oh my gosh, please don't hurt me.
So keep your eyes open and let's see where it goes. You guys don't look at me. Look there. If the ball is going to land somewhere prediction is working. If not, sometimes things go wrong. You never know. So look, how was that?
Hit like right here,
Right there?
right there.
Wow! Isn't that amazing? Right here. And we have all this arrow here, right? So maybe we can shrink a little bit. Let's try again. Oh, I changed the angle a little bit. Let me check. It's 45. Let's try again. How was it?
Are you closer?
Oh, where's the ball? Now let's try 30 degrees. We said was going to be, shorter, right? So let's try 30 degrees. And let's measure that. So make sure you mark the point now. So we're going to measure for 30 degrees, and then I'd like you guys to do a calculation right now for 30 degrees, what's going to be your estimate, okay? And then we're going to see if it matches whatever we're going to measure. So you place this thing now wherever the ball is, okay? You guys ready?
Is that here?
Like that?
No, there's more. Almost 60, I'd say.
How much?
Almost 60.
60, so this is 2 meters here, 3, and 60, 3.6. So that's what we got measurement, the measurement we got. So let's see if you can calculate from here, and you let me know. All right?
It would hit somewhere around 3.64.
6.4,
Yeah.
so we got pretty close. Okay. Thank you, you can stop.